Okay, everybody, here we are, chapter 2. This is the chemical level of organization. So this is section 2.1, so it skips a few pages and when you start chapter 2, and then it will jump right into it, okay? Now, I should point out that as you are going through this material, you actually need to make sure you are making a list of vocabulary words as you go. So as you're reading through, just write the word down and keep going. So all the stuff that I kind of hit, you need to make sure that you're hitting. Of course, you should be reading the whole section or all the chapter, unless we get to a spot where I say, don't worry about that, let's move on, okay? All right. So chapter 1, make you a vocabulary list. Chapter 2, make a vocabulary list, okay? All right, so let's jump right in. Let's jump right in and get started. Okay, so chemistry. All right, so our study of human body begins at the chemical level organization. So chemistry is the science that deals with the structure of matter, which is defined as anything that takes up space and has mass, which is to say mass, the amount of material in matter. So the space, how much it takes up. And a physical property that determines the weight of an object in the Earth's gravitational field. So it'll change. That will change in on a different planet. Okay. For our purposes, the mass of an object is the same as its weight. However, the two are not always equivalent. In orbit, you would be weightless, but your mass would remain unchanged. So it's taking up space. Now again, those two are equal on the Earth there. Okay. The smallest stable unit of matter is called the atom, or atoms, which we talked about before. And these have subatomic particles, which are protons, neutrons, and electrons. Protons, neutrons, and electrons. Right. So here is the typical atom. There's a proton, which is a positive charge. Proton is positive, P for positive. Electron, which is negative, and a neutron, which is neutral. As we look at we can just talk about basic elements, which we'll talk about here in a minute. They are equal electrons, equal protons, and equal neutrons, okay? All right. Now, so you guys don't get excited about chemistry. We're not going to get into it that much. There's a little bit here, but not that much. Okay, so if you look here, that electrons are so much smaller than protons. They're 1 in 1836 as massive. So when we consider the weight of protons and neutrons, or atomic weight, we do not consider that with electrons, right? So that is not part of it. Okay. All right, so electron shells and the shell and valence electrons as far as the orbit, okay? So the electron cloud is what it normally is. So when we see an electron, it's normally this cloud. But it doesn't help us to know that that electron can be anywhere in that cloud. So we end up with this thing what we call valence electron shells. We do it shells. We say the electron is this far away from the proton, which this is an energy level, by the way. And then it has this first shell. Okay? So again, protons, neutrons, and electrons. This is the real world, a cloud like a dodgeball, all right, with nucleus on the inside, right? And then what we use is the valence electrons or the shell, okay? Now, normal hydrogen atoms, H hydrogen normally has a proton and an electron with no neutron. All right, if it has a single neutron, it's called deuterium, and if it has 2 neutrons, it's called tritium. Okay. All right, so let's back up for just a second. Okay, so the atomic number is the number of protons. Now I have a periodic table here for that. This wants me to, I love advertisements, right? Okay. All right, so as you look at this periodic table, and I just pulled up one off the internet, only because normally we have one in the classroom, so it makes it a little easier. So this is normal periodic table. These are what we call noble gases over here. They're inert. So you can see neon, argon, krypton, xenon, light bulbs, I mean, this stuff. So everything is trying to be like these guys. We'll explain that in a little bit. These relate directly to the shells. Now, some of you guys know how many electrons are in the first shell? Maybe we get half. Let me move back here real quick. Elements and isotopes. All right, so if I change the number of neutrons, we change the number of, we call it an isotope. But, so I'm getting a little bit ahead of myself. We'll get back to the shell in just a second. Principal elements, and of course, if you go back to the periodic table, those are all the elements in the world, but those are, we're only going to be talking about a select few of them. We're not going to get into all those. So you see here, oxygen through phosphorus. So you need to learn the oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. Okay, it's down to 1.0. So this is percent of total body weight, and how much of your body is made from water, and what's the symbol for water? Water is what? H2O, right? H2O. Okay, so 2 hydrogens for 1 oxygen. Okay, so oxygen is 65 and hydrogen is 9.7. So roughly about 75% of your body is water, right? Okay, so percent of the body is roughly 75% water. Okay, so you need to learn down through phosphorus then. If you change the number of neutrons, again, protons, neutrons, and electrons, so neutrons with neutral charge in the middle, so we call it an isotope. So these are isotopes of hydrogen. So this is its normal. This is with 1 neutron, that's deuterium, and 2 neutrons, it's called tritium. So if I said carbon-13, carbon would normally be 14. I'm sorry, carbon would normally be 6, right? But the weight is what? The atomic weight is protons and neutrons, not electrons. So 6, remember, protons, neutrons, and electrons are equal. So 6 neutrons, 6 protons is 12. And this periodic table actually doesn't have the weights here. But if you had one that had the weights, so protons and neutrons for this number right here. So this is the atomic number right there. Number of protons. Number of protons. Okay. So atomic weight. Typical oxygen has atomic number of 8 and contains 8 protons and 8 neutrons. The mass number of this isotope, there it is right there, is 16. Okay. And of course, remember we said 8, 8, and 8. I'll let you read all that. So what is a mole? All right, so we have to give these weights to, everything has to have its own weight. So we use a standard number for any element, a mole. It's a specific quantity with a weight in grams equal to the element's atomic weight. So what we do is we take 600 billion trillion, or 6.023 times 10 to the 23rd. So if you go scientific notation, that's a lot of zeros back here. 600 billion trillion. And we call that Avogadro's number. But elements weigh, each one individually weighs a different amount. So if I take this number and multiply it by its individual amount, we get a different weight. That's why carbon and hydrogen and oxygen and xenon all weigh differently. Because of this, in conjunction with which one, how much each one of those weighs. Remember, we're talking about protons and neutrons together. Okay, protons and neutrons together. All right, this is called Avogadro's number. I always call it Avogadro's number. I don't know why I do it. Maybe it's something I don't remember. All right, so Avogadro's number is 6.023 times 10 to the 23rd. Okay. So we have next was, we're going to talk about the valence shells now. We have valence shells, we have valence electrons. So how many electrons can the first shell have? All right, so is you look at this right here, okay? What you see is lithium has an atomic number of 3, which means what? Number of protons, right? It has 3 neutrons, 3 electrons. So the first shell can only have 2 electrons, right? The second shell can have 8. So this only has 1. Okay, that's okay. That's what it is. This one, neon, remember this is a noble gas. It's all the way to the right. It's completely filled in the second shell. Okay, that's a clue to the periodic table. Let's shoot over there real quick. Okay, so we said before neon had 8, right? How many in the first shell? So we do a proton. The nucleus, rather. Right? We have a shell. And we have another shell. Let's do one more shell. Okay, so how many electrons do I have in the first shell? 1, 2. How many? Let's see the dots. Next shell is how many? Maxed out. 8. And then how many in the third? So if you don't know, you don't have to guess. 8. Okay. So if you look at the periodic table, how many in the first shell? 2. Look. 1, 2. How many in the second shell? 1, 2, 3, 4, 5, 6, 7, 8. How many in the third shell? 1, 2, 3, 4, 5, 6, 7, 8. Now, can you guess how many are in the fourth shell? How many in the fourth shell? Now, if you can't see this, you look right here, it's 18. So instead of counting all this, it's 18. 1 through 18. So in the next shell, I have 18 electrons. Okay, so that is how we do valence electrons. Now, this is important when it comes to different types of chemical bonds. So some chemical bonds will actually use electrons to make themselves up. So we know that water, H2O, is actually oxygen and hydrogen, supposed to be an H, and hydrogen bonded together, right? So we actually end up with HOH. So this is like the chemical formula of water. These bonds bonded together, and they use different electrons or different methods of combining to make that element or that molecule compound. Okay. Again, don't guess. It's right here in the periodic table. 2 in the first, 8 and 8. 2, 8, and 8. Okay. All right. Let's get back to this. All right. So this shows neon, which was all the way to the right of noble gas. And if it's all the way to the right, obviously, if you're counting up to figure out how many electrons you have in the last or that shell, 2, 8, and 8. Okay. All right. By the way, you guys should be using YouTube for a ton of stuff. You guys should be using YouTube for figuring all this stuff out. If you don't understand it, go to YouTube and pull it up. Someone has created a video for you of that. There's no doubt. Okay, so make sure that you're going to YouTube to figure this stuff out. Okay. All right, so molecular weight is just adding up the different molecules. Okay, so ionic bonds. So now we have ions. Ions are charged particles. Of course, if we say charged, we're talking about positive and negative or neutral, right? Right. So ions are definitely charged particles. Okay, so we have a cation. The T makes a positive, right? So that's a positive ion, or cat is positive ion. So cations are positive, and an, in medical terminology, an is without. Right? So this is an anion. Okay, so an anion. All right, so positive and negative, and of course, in this stuff, opposites attract. Okay, so ionic bonds are the charged particles and opposites attract. All right, so one atom is an electron donor, loses one or more electrons, becomes a cation. So if you have an atom and it lets go of an electron, it becomes more what? It's a charge of an electron. If it lets go of that electron, it becomes more positive. If you let go of a positive, it becomes more negative. Okay? So look at it as in who's the electron donor, who's the electron acceptor. Okay? All right, so we like to look at sodium chloride, which makes this nice little cubes or salt cubes. Right? So sodium chloride is salt, by the way, table salt. It is a fantastic bonding thing, and it uses an ionic bond, okay? So it uses the opposites attract, okay? The opposites attract, sodium chloride, okay? All right, sodium, just as a quick, show you why this works so well. If you come over here to your periodic table, I just want to show you this real quick. Where is I give one away, where does it go? If I add one, where does it go? Okay, so sodium, they all, remember I said before, they all kind of want to be like this. So that's why these opposite attracts work so well. Okay, so they work well that way. Okay, all right. All right, so opposite charges attract sodium chloride. A positive charged sodium likes to do what? All right, likes to attract to the negative chlorine, okay? All right. All right, next is covalent bonds. Now, ionic bonds are medium strength. In other words, can I pull sodium apart? Right, can I take sodium? Can I take sodium and just pull it apart? Okay, but what happens? What do I do if I put sodium into water? What do I do if I put it? What happens to it? Right? It dissolves. It actually makes what we call an electrolyte. All right, so it dissolves. So they dissociate. Sodium chlorine, a salt, will dissociate in water. It comes apart, which we'll talk about that more later. All right, so that's how we break that apart. So it's kind of medium strength. I mean, I didn't have to like beat it up. I mean, I didn't have to blow it up. Okay. But I just had to add it to water and then dissociate it. Okay. Now, covalent bonds are very strong bonds. All these are all the things around you, your pens, the board, the writing board, your computers, all that things are bonded together through what we call covalent bonds, okay? And these are covalent bonds right here. They are, okay. So this is covalent bond, So each one of these lines represents the sharing of an electron. Now we said hydrogen wants to be, this is hydrogen, right? H2 wants to be like what? If you look at your periodic table, you see it wants to be like helium, which helium is a known gas. It's on the right. How many electrons in that shell? 2. Remember, helium is just has 2 electrons, right? 1, 2 on the periodic table. Right? So hydrogen wants to be like helium, so this hydrogen says, let me borrow that electron for a minute, and I'll be like helium. And then this one says, okay, well, it might come out. So then these guys are happy, they're satisfied, right? So H2 is like helium in its properties, it's still hydrogen. Okay, so this is, remember, this line represents 2 electrons. Each line represents 2 electrons. So this, if that's 2, how many is that? That's 4, right? Okay, and how many is that? And what is that? 2 oxygens and a carbon, that's what? That is CO2. Okay, so let me come over here to the periodic table real quick. Okay, so CO2. Right, so you see the oxygen there, right? Wants to be like neon. So each line represents 2 carbon needs to be like neon. How many electrons does carbon need? 2, 3, 4. 1, 2, 3, 4. Now, how many does oxygen need? 1, 2. 1, 2. Right? 1, 2. Okay. Does that make sense? Okay. So CO2, which is a byproduct of what? Respiration, right? CO2, not this is what? What is that? Where do you find that? That's carbon monoxide. This is from burning. Anything that burns gives us carbon monoxide, like our cars, campfires, whatever. Okay. All right, let's go back over here. All right, so we have what you have there, that hydrogen, that H2, that is a single, that polar or nonpolar. That is a nonpolar molecule, okay? If it has a shape to it, in other words, this is symmetrical. This is organic chemistry, by the way, guys. This is writing it like this. So it is symmetrical, right? Flip that over and it'll look the same, so on and so forth, okay? So this is a nonpolar single covalent bond, nonpolar double covalent bond, okay? Nonpolar triple covalent bond. All right. Now what is water? Look at this over here. Is that symmetrical? Right? Is that symmetrical? Remember, these are sharing electrons, right? Right? They're sharing electrons. Okay, so it's polar. It actually ends up with a charge. With a charge to a water molecule. Okay? All right, and then, by the way, when we talk about that next, that is, well, how we'll describe that. So that water then is a polar covalent bond. Polar covalent bond. Now, water molecules to water molecules. Okay, so these all attach together. This is what is called a weak hydrogen bond. Now, this is a water molecule. Well, you know it's weak by what? You pour a glass out, you take a drink, whatever, you separate a water molecule. If you jump into a pool, we have little water bugs and ants or spiders or whatever go across the surface of the water. That's called surface tension. That is this bond right here. That is called surface tension, right? And that is that bond. We know it's weak because I can't walk across water. We only have one person that could do that. I tried. Anyway, so that is a weak hydrogen bond. Now, remember what I said. Ionic bonds are kind of weak. They're medium strength. Covalent bonds are very strong bonds. To get this board apart, I'd have to cut it, right? Or grind it up or do something like that to get it apart, okay? And hydrogen bonds are very weak bonds, okay? Okay, this is talking about nonpolar covalent bonds and polar covalent bonds, and here's that example, water and hydrogen. So you see you have a net charge. This is charge right here, right there. That's the charge, positive and positive. So you end up with that positive line there and that away, okay? Hydrogen bonds, here's what I was describing. These weak hydrogen bonds right there, okay? Surface tension. States of matter, solid, liquid, gas. I hope you guys already know that. All right, so let's talk about some of these. We've got a bunch of definitions here. So next we're going to talk about decomposition, synthesis, and exchange reactions. Okay. All right, so chemical reactions. Cells stay alive by functional and controlling chemical reactions, which is metabolism. In a chemical reaction, new chemical bonds form between atoms. Existing bonds between atoms are broken. These changes take place in atoms where the reacting substances called reactants are rearranged to form different substances called products. So if I'm taking whatever I'm starting with is the reactant, what I end up is the byproduct or the product. Okay. The byproduct is also could be called metabolism or metabolites. Okay, metabolites. All right. Here's that metabolism. So all of the reactions in the cells of tissue of the body at any given moment make up its metabolism. And the byproduct of metabolism is metabolites, which we talked about the urinary system, and it gets rid of waste products by, right, going through that process, metabolites. So the kidneys pick up the metabolites and excrete it. All right, so basic energy concepts. Work is the movement of an object or change in the physical structure of matter. In your body, work includes movements such as walking, running, and also organic molecules and the conversion of liquid water to water vapor. Energy is the capacity to do work. So the movement of physical change cannot take place without energy. So work is the movement. Energy is what's required to get it to the ability or capacity to do the work. There's two types of energy we need to discuss. Kinetic and potential energy. All right? Kinetic and potential energy. So kinetic energy is the energy used to climb a ladder or taking this can and lifting it up in the air. I've stored the energy now in this can, and when I release it, I let it go. Potential energy is stored. Kinetic. Potential energy is stored. Kinetic energy is we release it. So kinetic energy is movement. So I store it, or potential energy, and kinetic energy is when we drop it or release it. So kinetic energy is the energy of movement. Potential is where we store it. I hope that's clear. I don't think I messed that up. I think I mentioned that is covered, right? Okay. Anyway. All right. So now we have to take this energy and we're causing it to do, we're going to make it change reactions. We're going to do some decomposition. Of course, now decomposition means to what? To break things down. Okay. So decomposition means to break things down. So a decomposition reaction. So use AB. Okay, use AB. All right. So just a quick and easy one. If I did, let's try very simple. NaCl yields Na plus Cl. So that would be, you'd see we're breaking down sodium chloride into sodium and chlorine. Okay, sodium chloride. Okay, so you just use the letters for right now just to help yourself understand what the process is. Okay, all right. So the decomposition is to break it down. When we break things down, it's called catabolism. Okay, see catabolism right there? Catabolism. So when we break things down, it's called catabolism. All right. Hydrolysis. So water lysis. Lysis means to break apart. Okay. So water loosening reaction. What I want you to do, anytime you see this, is to add in the water on this side where it's combined, and where the A and B are split, A plus B. I want you to add a hydrogen and a hydroxide. So what is water? H-O-H. Now what did I do to the water? I actually did what? I hydrolyzed it. I broke it apart. So when you break apart the water, you end up with hydrogen and a hydroxide, HOH. Okay? This is a hydrolysis reaction. So it's a decomposition hydrolysis reaction, which is called catabolism. Here's the process to break it down. All right, next we have a synthesis reaction. A plus B yields AB. All right, you can see we're building this up. And what did I ask you to do? I asked you to put water and hydrogen and a hydroxide in here, right? So put water on the AB side, connected, and a hydrogen and a hydroxide on the other side. Here it is. AB plus, that's not supposed to be. That's not okay. So this is supposed to be what? What is that being supposed to be? That's supposed to be an H. Right? Does that make sense? Yeah, that's supposed to be an H. Yeah. Okay, that's confusing. That's right. I don't know if your book has that or not. So that would be okay. All right. So there's your hydrogen, there's your hydroxide, we're making water there. Okay. All right. So A plus B yields AB. Okay. A plus B yields AB. This is hydrogen and hydroxide makes the water. Now, what do we do when we build things up? It's called anabolic or anabolism. Like anabolic steroids make people really strong and big. Right. So it's built. So it's anabolism. All right. Now, what have I done to these two A and B? This A plus B. I've taken the hydrogens out, or I dehydration synthesis, or I dehydrated it. Right. You can also imagine this is our product, right? So these are the reactants. This is the product plus water. Now this water is free to go do whatever it wants, right? So you can actually release that. If you're exercising, you can release that water to go do whatever it wanted. And if you release water when you're exercising, you're doing what? You're dehydrating. Okay? Right. So but remember that this is, if I take the hydrogen or hydroxide out of the two reactants and I make water with it, I dehydrate it. Okay? That's anabolic. All right, so this is showing you an exchange reaction. Of course, you can just follow the letters there for that. And then here's a reversible reaction. It's reversible by these arrows right here. Okay. So we said before that when I was reading this, I said A, for example, A plus B yields AB. So I'm saying going to the right, we're making or synthesizing, which has names, right? This is what's happening if I add in the hydrogen hydroxide, I'm dehydrating to the right, and I'm doing what? Hydrolysis to the left. All right, so anyway, yeah. So anyway, A plus B yields AB, or AB yields A plus B. Now we have a formula that works really good there. So ADP plus P yields ATP. Right, now that formula right there, this is what our body uses for energy right here. It's adenosine triphosphate. So it is reversible. Okay, so anytime we use energy, it has to go. When we use the energy, it goes here, and when we're trying to put it back to energy, it goes that way. Okay. Of course, you can add your hydrogen, hydroxide, and water there too, which will then help you understand what that formula is doing. All right, so what are enzymes? Enzymes speed up reactions, or they are what? They lower the activation energy. So here it is. So the energy of activation, or activation energy, is the energy required for this to go through, for this product to make this product here, okay? So AT, or ADP plus phosphorus, plus phosphates, rather, yields ATP, all right? So that is a stable product at ATP. We have enzymes that will help this process. So with the enzyme, it lowers the energy of activation. Right? We end up with ADP plus the P yields ATP, and then you see an enzyme right here. They would call it. They put that right on top of that arrow. Now, this enzyme only works for this. You would actually have a different enzyme going back this way. Enzyme 2. So enzymes are very specific. They only work in that one process. Okay, they only work in that one process. Okay. So there it is right there. There's your enzyme. This is showing you a pathway. A plus B, A yields C, and C is blah, blah, blah. Okay? I think that's supposed to be B also. Let me shut that light off again. Okay, so that's enzymes that lower the energy of activation. Lower the energy of activation. Are very specific. Also, don't destroy them in the reaction. So they get used over again. Definition stuff. Reactions that release energy are said to be exergonic or exit, and reactions that absorb more energy than they release are called endergonic. All right, so inorganic and organic compounds. Inorganic compounds lack carbon, and organic compounds always contain a carbon. Now look. This is CH4. Okay? It is the smallest organic molecule that we have. Organic molecules all have a what? A carbon-hydrogen bond. They must have a carbon-hydrogen bond. Okay? What is this? Carbon-hydrogen bond? No, this is hydrogen chloride. This is an acid. Right? That is not. This is chlorine. Okay? What is this? Carbon dioxide, right? So you see a CH bond there? No, this is inorganic. What about this? Right? So that is what? Water. Right? So there's no carbon-hydrogen bond. What is this? Sodium chloride, that's stable salt, right? Okay, so you see they have to have a carbon-hydrogen bond. Okay? So two major classes of compounds are nutrients and metabolites. Nutrients are the substances from food that are necessary to form physiological functions. Nutrient includes carbohydrates, proteins, lipids, vitamins, minerals, and water. Metabolites are the substances that are involved in or the byproduct of metabolism. There's your inorganic and organic compounds. So here is the most important inorganic compounds, which means what? They don't have a carbon-hydrogen bond. So carbon dioxide, oxygen, water, acids, bases, salts, those are all inorganic compounds. All right, so physiological systems, our bodies, depend on water. Almost every single reaction in our body needs water with it, okay? So some examples or some, anyway, water is the most important object or substance in our bodies. Okay, so water is also described as a universal solvent. Okay, water is a universal solvent, right? So for what does that mean? Water can actually dissolve or dissociate items. Okay, so to make up a solution, first of all, you need a solvent, a universal solvent called water. Right, there's your solvent, and then solutes. Right, so something that would make up solutes like sodium chloride, which is table salt, which is going to have a bond, will dissociate, split apart, and in solution or with a solvent to make up a solution. So to make a solution, you need solvent and solutes to make a solution. Reactivity in our body's chemical reactions take place in water. That's almost every reaction. Okay, hydrolysis or dehydration, which is what we just talked about. Water has a high heat capacity, is the quantity of heat required to raise the temperature of a unit mass of the substance 1 degree. Water has a really high heat capacity, which makes sense, which is great because we don't want our body temperatures to change very fast. This is exactly why babies have such a hard time with temperature. They get too hot, they get too cold, because they're little tiny little nuggets, right? They're little nuggets. And it doesn't take long for that heat to transfer either out or in. Okay? So the temperature of water must be quite high. So this is when we boil stuff, right? When we boil stuff, we have a thermal inertia, which is, you know, I've heard of what's called boil stuff, because you have to break all those hydrogen bonds, H2O, and then that's hydrogen bonded to another water molecule that the water will show, and then those have to break. Once that breaks, they don't have right? So that is, you have to break all those before you start getting steam, okay? All right. Let's see. Okay, water carries a great deal of heat away when it changes from liquid to gas. This feature explains cooling effect, perspiration, and skin. So water carries a great deal of heat away when we're sweating, right? So as it leaves, it's carrying that heat away. All right, also water is a great lubricant. There's that thermal inertia right there. Okay, so water is a polar molecule. All right, so now, when I put water into, when I put salt into water, we said it dissociates. Here's that dissociate. Now, what does that mean? That means the sodium chloride NaCl splits apart. Remember what kind of bond is NaCl? It's an ionic bond. And when that splits apart, it makes a sodium and a chlorine. A sodium and a chlorine, which is what? Cation and anion, right? A cation, positive, and an anion, negative. Okay? All right, so those dissociate, so they don't dissolve. Everyone says, oh, the salt dissolved in water. No, it didn't do that at all. It dissociated. Okay? Now, when I take something, remember, these charges are actual electricity, right? Electricity. They are electricity, right? So they're positive and negative electrical charges. So when I dissociate them into water, we actually make what's called an electrolyte. Electricity, right? Electrolyte. Okay? Our bodies need electrolytes to function. This is actually how we perform work. So away from zero is either positive or negative. And if that's zero, there's no ability to do work. There's no potential energy. If I go away from zero, become positive or negative, there is a potential to go back down to zero, which would, if it does actually, would be what? Kinetic, right? The actual motion. Okay. Anyway, we dissociate and we end up with these charges. By the way, that's how we get muscles to contract, and that's why if you're outside sweating too much, you get that salt ring on your hat. That salt coming out of your body is you losing electrolytes, which you have to replace. You cannot just drink water when you're sweating. You must have replace your electrolytes. Okay, all right, so here's some important electrolytes that dissociate in body fluids. You have to memorize these. No. There's sodium chloride, which we talk about all the time, potassium chloride, and all those other ones there, okay? All right, let's talk about hydrophilic and hydrophobic compounds. So what is phobia? Water fearing, okay? Hydrophobia, and so phobia is a fear. So hydrophobic does not like water. Hydrophilic is water loving. All right, now, so water is, we already said it's a solvent, right? It dissolves things. Does water remove oil? So the answer to that is no. And that's because oil is what? Hydrophobic. So it'll only dissolve things that are of like. So water will dissolve anything that is hydrophilic. It will not dissolve things that are hydrophobic. And oil is hydrophobic. So for example, if you get oil on your shirt, the only way is not to put it in water, it's to put something that we call an emulsifier on it, or something that will actually break up the oil molecules so that it then can be washed away. Okay, your gut does the same thing. Your body does the same thing. We have in our body an emulsifier. So when you eat your cheeseburger today, or your French fries, or whatever it is you're eating that's greasy today, butter. Okay, it's oil, right? We can't avoid oil. We need it. We need the cholesterol. But how do we deal with it? Okay, we actually have to use an emulsifier. And on our body, anyone know what the emulsifier is? It is bile, right? That comes from our gallbladder, from our liver, right? So bile is an emulsifier. This is why when kids get out of the shower, how many of you guys have kids or grandkids or whatever, brothers, sisters, they get out of the shower and they're still dirty, right? And you kick them back in there and say, you need to use soap this time, all right? Get back in there and use soap. That's because soap is going to emulsify the oil so that we can get that trapped dirt out of the oil and get it to go down the drain. Okay, that's why we need soap. For all those that shower, that don't shower with soap, that's why. Okay, so now you know, now you need to use soap. Okay. Okay, so colloids and suspensions. All right. All right, so a colloid or a suspension. So a colloid is something that will not come out of solution, or it continuously stays in its mix. Okay, it continuously stays in its mix. Now, a suspension is something that contains large particles in solution, but if undisturbed, the particles will settle out of solution. What is our blood? Is our blood a colloid or a suspension? Okay, what is our blood? All right, well, if you let our blood sit long enough, it separates. Okay, it separates into the buffy coat, to the plasma, and to the blood cells. Okay, so our blood is a suspension. A colloid would be like Jello. There's always room for Jello, right? Anyway, and it doesn't come out of solution, so long as it sat there, it wouldn't separate. Okay, so that's a colloid and suspension. Okay, so this formula right here, H2O yields H plus OH, or HOH yields H2O. Obviously, that is going to the right it breaks it down, right? So it's a decomposition. Going back the other way, synthesis. All right, so HOH, so pH is percent hydrogen. So, and this is basic. This is a hydroxide. So anything that's a hydroxide is basic. Anything that's H is hydrogen, it's acidic. All right, so when we look at the pH scale, let me come down here real quick. As you look at this, you see percent hydrogens and you see percent hydroxides. Okay, so anything over here is more acidic. Anything over here is more hydroxide. Okay, so stomach acid is extremely acidic. Okay, saliva is slightly acidic. This is neutral. All right, 7.34, 7.35 to 7.45 is our blood. Right there. Okay, 7.35 to 7.45 is our blood. That's an important number. You should know that. Right, and anything to the right of that is very basic or alkaline. Okay, now each one of these steps represents a factor of 10, which means what? It's times 10. 10 times 10 times 10 times 10 times 10 times 10 times 10 of hydrogen molecules, okay? So in this situation, what is 1 as compared to 3? It is 100 times more acidic, 10 times 10. What is 1 to 4? 1,000 times more acidic, 10 times 10 times 10. Okay, so will you ever have a 2, a 3, a 4, a 5, followed by zeros? No. Remember, 1 times 1 is always 1. You'll never have a 2, so don't get that confused. That's a distractor on the test, right? That makes sense? Okay, so, all right, so pH. Pretty straightforward, not crazy. Acids, bases, and salts. I want to show you this one down here. This one right here on the bottom. So acids, bases, and salts, they dissociate in water. They have their important roles to make buffers, which maintain your pH. So a buffer actually maintains its level. So buffers will stabilize your blood pH around that 7.35, 7.45. So we have proteins in the blood and other things that actually cause it to stay right there. If we get too high or too low, we can go from muscle cramps to loss of consciousness, can't move our muscles, things like that. So if our pH changes too much, that's a bad thing. Right? By the way, if we change the pH of a solution, what do we do to proteins in your body? It's called denature. So frying an egg denatures that protein. It changes its shape. And as we will see here in a little bit, proteins, the most important thing about proteins, the most important information or thing about proteins is its shape. Right? So it actually has that organic molecule shape to it. And if you denature it, you change its shape, it is no longer functional. It's like an enzyme. Enzymes are proteins. And if you change the shape of an enzyme, it doesn't fit onto that molecule. Okay. So I wanted to show you this. This is hydrochloric acid and sodium hydroxide yield water and salt. anytime you have a strong acid, strong base, it yields a salt, and a water. Okay? So what type of reaction is this? What type of reaction is that? That is A, B, C, D, yield A, C, B, D. What type is that? That is an exchange reaction. Okay, from earlier, that is an exchange reaction. Okay. All right, let's go ahead and move on. All right, so living things contain organic compounds, which are what? Carbon-hydrogen bonds, right? Made up of monomers, polymers, and functional groups. Monomer is a molecule that can be bonded to other identical molecules to form polymers. Okay, so I'll let you read that. Don't get into the organic compounds. I'm not going to ask you about amine groups and carboxyls and hydroxyl groups and all this. I'm going to ask you these guys here. Not super cool. We're not going to get into chemistry that much. I know you guys are like, yay! Yay, no chemistry. Well, not much, a little bit. Carbohydrates, 1-to-1 ratio. All right, the most important carbohydrate that we need to talk about is a monosaccharide called glucose. Its formula is a 1-to-1 ratio. Okay. I'll just get my hand on that. Okay, a 1-to-1 ratio. Remember carbohydrates? What are carbohydrates besides the devil? Right, they're sugars, okay? They're sugars. So a monosaccharide, the most important that one that we talk about all the time is called glucose. Glucose. Its formula is a 1-to-1 ratio. C6H12O6 is a 1-to-1 ratio. Carbon, hydrogen, oxygen. Remember we said about hydrogen bonds? There it is right there. C6H12O6. That's it right there. You don't have to learn the organic shape of that. That's not what we need to do, right? That's a whole another class. But you do need to know glucose is C6H12O6. That is glucose. That is what we use to make ATP, adenosine triphosphate, which I said before, which is the body's form of energy. There's a couple more, but that's the primary one. Okay. So disaccharides and polysaccharides. Okay, so a disaccharide is sucrose. That's our table sugar. So disaccharide is our table sugar. So two monosaccharides joined together form a disaccharide. So if you eat table sugar, you're converting that into energy, right? And if you don't use that energy, it goes stores as fat. Okay, or adipose tissue. Okay. So this will help. Look, put the plus here, and then this is here. So this is A plus B yields AB, and this is AB yields A plus B, and then you see our dehydration synthesis and hydrolysis, and of course you can add all that other stuff in there like catabolism and anabolism, right? Okay. Okay, so a polysaccharide that we talk about a lot is glycogen. Glycogen is what we use to store glucose. Okay, we store glucose as glycogen. Right, that's part of the muscle process, which we'll talk about that when we get in. Here's a nice little table. This will help you understand what we just talked about there. Make sure you go through that. Lipids is a 1-to ratio. Saturated and unsaturated fats, the only difference in the two is this double bond right here, okay? Of course, this will show you there's a table in here or a chart that talks about the different types of whether saturated or unsaturated is good for you and why. I'll let you read that. Okay, all right, so triglycerides are one that we talk about. That is a lipid. We have another one that we talk about. What other lipid do we talk about? Steroids, right? So testosterone comes from cholesterol, okay? The steroid cholesterol will help make testosterone and estrogen, okay? So you can see why cholesterol is so important in our life. Now, we have to have cholesterol when our livers make cholesterol, but we also get a lot of it from our diet. So too much is not good, but some people have a high propensity to make a lot of cholesterol in the liver, and some don't. So the ones that don't will actually have lower cholesterol levels, even if they have a chronic diet, okay? Some that have really make a lot of cholesterol in their liver, also have a fatty diet, will have really high triglycerides, really high cholesterol levels. But remember this, that steroids, cholesterol, and triglyceride estrogen are all a lipid. Okay, so lipid, or fats, right? Adipose tissue. Okay. When we get into chapter 3, we'll talk about phospholipids, which is a polar head and a non-polar tail, which when I said polar before, I was describing it in water, right? So a polar head and a non-polar tail. Okay, a polar head and non-polar tail, which means to say that if it's polar, it's like water, which means what? Non-lipid, right? Okay, so oils and fats are lipids, right? So polar head, like water, is non-lipid. Tails, which are fatty acids, okay? All right, so when we talk about the phospholipids, this is describing a cell membrane, which we'll talk about in chapter 3, cell membrane. And there's your phospholipid right there. So hydrophilic likes water. Hydrophobic tails does not like water, right? Likes oil. Okay, proteins. Now, proteins are arguably the most important group in our body. So proteins are the most abundant organic molecules in the human body, and in many ways the most important. There are gazillion different proteins. So what are some of the functions of proteins? There's support. Structural proteins create a three-dimensional framework of the body. Movement, contractile proteins. So this is for like your muscle, right? Actin and myosin, which we talked about earlier. Transport, we have transport proteins. Buffering, which remember stops the, remember I said we have proteins in the body, okay? That actually cause buffering, which maintains the pH. Metabolic regulation, many proteins are enzymes, which we talked about, right? Enzymes are very specific shape. So the most important thing about proteins is its shape. Coordination and control, protein hormones, remember this is part of the endocrine system for long-term regulation, right? Defense proteins, this is our immune system. We have tough, waterproof proteins of the skin, hair, nails, protect the body from environmental hazards, immune response. Clotting proteins restrict bleeding after injury. Protein structure, what's the building blocks for protein, which is called amino acids, right? 20 different amino acids monomers occur in significant quantities in the body. All 20 amino acids are small water-soluble molecules. Typical protein contains 1,000 amino acids, while the larger protein complexes have 100,000 or more. All right, so anytime you hear peptide bond, that's how we put those amino groups together, or amine groups together, right? So connecting these guys together is a peptide bond, which here's that reaction, dehydration synthesis or hydrolysis, okay? Peptide bond connects these two amino acid groups together. Now, what I said before, protein, the most important thing about proteins is its shape. Is its shape, right? Is its shape. All right, so if you can look at it like in and out of the board this way, that would be tertiary, primary, secondary, tertiary. And then if I took this tertiary figure and folded it in on itself, we get this quaternary structure. Okay? So primary, secondary, and tertiary, and quaternary. Okay? Quaternary just means full. Okay? So primary, secondary, tertiary. Now I got three-dimensional object, and all the memory we said before that elements all have a charge to them. So then these guys will react with each other. They'll fold in on themselves, and then we have this very specific shape of a protein, right? A very specific shape, like an enzyme or whatever. It's very specific in its shape. If I heat it up or denature it, it changes its shape. That protein is no longer functional for its job, whatever its job was. Okay, so primary, secondary, tertiary, and quaternary structures of the proteins. Globular proteins like gamma globulin, globular, hemoglobin, right? Those are all tertiary proteins. And fibrous proteins, and this would be like collagen, straight, long, strong. Protein shape and function, make sure you read that. There it is, changing one of the 10,000 or more amino acids in a protein can alter the way the protein functions. Like sickle cell anemia, which is a red blood cell that's not in its correct shape, right? So it's not in its correct shape. All right, so we have enzymes. Remember, enzymes, they're proteins, right? So we have this thing called substrates. You can look at it like this if you want. A plus B yields AB. Okay, A plus B yields AB. So the substrates combine very specifically. Remember, this is showing you round, this is showing you like a point. Right? They actually fit into this protein right there, or into the shape of this protein, this enzyme, which does what? It lowers the energy of activation, makes it go faster with less energy, which is a good thing. Right? Combines it to make the product. So these are the substrates are also the reactants. The product then is created and then released. Once we create this product, it no longer can fit here and it gets released. Now this enzyme is not destroyed, it goes back, it does it again. So make sure you understand what the saturation limits are, specificity, regulation, cofactor and coenzymes. These are just things that help the enzyme. So some things, some reactions like our blood clotting cannot occur until a specific process happens. So a cofactor is an ion or molecule that must bind to an enzyme before substrates can also bind. Without a cofactor, the enzyme is intact but non-functional. With a cofactor, the enzyme can catalyze a specific reaction. Examples of ionic cofactors include calcium, magnesium, which bind enzyme active sites. Coenzymes are non-protein organic molecules that function as cofactors. Our bodies convert many vitamins to essential coenzymes. Okay, so let's move on. Here's that denaturing. So when we change the shape of a protein, it's called denaturation. Or denaturing that protein, it's no longer functional. Now listen, we can denature it by either heating it up or putting it in acid. So if you put something in acid, it's going to change its shape. Glycoproteins and proteoglycans are combinations of protein and carbohydrate, which makes sense. Carbohydrate that we talked about was what? Glucose, right? Glycoproteins and protein glycans, okay? Are combinations of proteins and carbohydrate molecules. So glycoproteins are large proteins with small carbohydrate groups attached. These molecules may function as enzymes, antibodies, hormones, protein components of plasma membranes. Glycoproteins and plasma membranes play a major role in identifying normal versus abnormal cells. So glycoproteins are our cell identity markers. So every one of our cells has an identity marker that tells our immune system that it's us. If it doesn't have that, our immune system will attack. Proteoglycans are large polysaccharide molecules linked to polypeptide chains. Just all this means is polypeptide is many peptide chains between many amino acids. Proteoglycan binds adjacent cells together and give tissue form that exhibits working consistency. Okay. All right, so DNA and RNA, pretty straightforward. Okay, so a nucleotide, so everyone knows that our DNA is in a double helix structure. Our RNA is not in a double helix. So DNA must have complementary base pairs. In other words, something must meet up with something as the other. All right, now, the basic building block for DNA is what we call nucleotides. Talking about RNA, just remove the T. Okay, that's it. All right. All right, so as you go through this, let's go to the double helix here real quick. So you see that A is always bound to T. G is bound to C, T is to A, and so on and so forth. Here's our double helix. If you uncoiled it, it would look like a ladder, right? Here's our hydrogen bonds there. Okay. This is how the DNA knows to put on the other side. And when we split this apart, put one half in one cell and one in the first cell. And this then we put the other side of that over, and then we have two identical DNA strands. Okay? That's how we continue or perpetuate our DNA in our living cells that must go through reproduction. Okay? A living thing. All right, this is how we pass our genes on to our family members. All right, so I'll let you read the difference in the RNA. Remember, nucleotides is the phosphorus, the sugar, and the nitrogenous base. That is the basic unit for DNA. Next, we have ATP, adenosine triphosphate. Remember, we talked about this being the energy source of the body. So the phosphate does not provide energy. This is not the energy. This bond right here is the energy. If I have this bond, it means that I have stored energy in what type of reaction? In an inorganic reaction, I've stored energy right there. It's called energy bond. If I break that bond, or I take this to this, if I do A, B yields A plus B, right? I release energy from the system, right? That's exergonic, right? And we use that energy to do whatever it is, muscle contraction or whatever. So a byproduct of that is heat. So remember, when we break bonds, it's not 100% transferable, but we actually create heat. So when you see this adenosine triphosphate, this we can break this one here. This becomes adenosine monophosphate. All right. So this is reversible, right? I said that already before. This would be ATP. Great formula here. There it is. I highly recommend you use this formula right here. This formula right here. So this would be like A plus B yields AB. But use this formula to answer all those questions. Okay? To answer all the questions like, is it hydrolysis or dehydration? Is it catabolism or anabolism? Is it exergonic or endergonic? Okay? So go through that with this formula right here. Now, something I didn't mention before, everyone knows what adenosine triphosphatase is, okay? Anything that ends in ASE, anything that ends in ASE is an enzyme. ATPase. Adenosine triphosphatase. So anything that ends in ACE is an enzyme. So if I said, what is glutathione peroxidase? You may not know what it does specifically, but you know it is a enzyme because it ends in ASE. So anything that ends in ASE is an enzyme. All right, so here is a nice table of organic and inorganic molecules. Make sure you look through that, it's pretty important. Okay, and that wraps up chapter 2. Okay, so make sure that you do the review questions. Make sure you do them all the way through 32. You guys should be listening to YouTube videos. You should be watching. You can watch this video that I just gave you here. You can watch it again and again and again. Okay? All right.